Okay, today we are starting definite integral, and there is a little bit of theory that we need to develop before we really learn the thing by solving problems. Okay, so let f be any function of x. Assumed to be continuous in the closed interval a comma b. Okay, divide the interval a comma b into a finite number, say n, of subintervals. So we are also writing not necessary. मी 4 लेक्चर लिहिलं नाही तर माझं हँडरायटिंग खराब झालं बघा. Not necessary equal by means of points x1 x2 dot 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 xn minus 1 such that a is equal to x0 is less than 1 is less than x2 is less than dot 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 is less than xn minus 1 is less than xn is equal to b. Let me write it completely and then I will explain you. It is very simple. This is called partition of interval a comma b into n subintervals. Let k1, k2, kn be any numbers such that x0 is less than k1 is less than x1, x1 is less than k2 is less than x2, and so on up to xn minus 1 is less than kn is less than xn. So we are taking any point in between. Okay, so what are we doing so far? Let me explain. So these are values of x. Suppose you have a somewhere here and B somewhere here. We call A which is equal to x0 and B which is equal to xn, and then you have n minus 1 points in between. So x1 not necessarily equal x2, x3, xn minus 1. Okay, so basically we are partitioning the interval a comma b into how many parts? N parts. N minus 1 points between a and b gives us n parts, and then we are taking any point here as k1, k2, any point, k3. Okay, this is what is the meaning of whatever we have written so far. Now consider the sum. S is equal to, you evaluate the given function f. F is a continuous function defined over a comma b. So evaluate f at k1 multiplied by x1 minus x0. Add, evaluate the function at k2 multiplied by x2 minus x1. Add, evaluate the function at k3 multiplied by x3 minus x2 plus dot 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 plus evaluate the function at kn multiplied by xn minus 1. Suppose we consider this sum, which in sigma notation we can write sigma r goes from 1 to n f of kr, okay, into xr minus x1. Okay, and again you can write it by making it further look good. R is equal to 1 n f of kr delta r, where delta r is equal to xr minus xr minus 1. Okay, so this is the setup. This is the setup, and this is much before calculus. I mean, this is something which is very, very early. Calculus is 300 years before Newton, Shivaji Maharajanचा काळ. What we are trying to discuss right now is much earlier than that. Maybe I will draw another picture and try to. Okay, here itself, suppose I have a curve like this. This is your x-axis, this is your function. Then what are we trying to do? We are trying to find out the value of the function at k1. This multiply by x1 minus x2. So this. Area. Okay, so this is the area of this rectangle. That is our first term. What is our second term? Our second term is evaluate at k2. That is this point. Create a rectangle. This is our second term. This one. What will be our last term? Evaluate at kn multiplied by xn minus xn minus 1. This is our last term. And like this, there will be many rectangles in between, something like this. Something like this. Okay. Whatever. So that is what is the. So if we want to give geometric interpretation to this as, it is the sum of the areas of the rectangle that we have created, n rectangles. Okay, this is sum of the areas of n rectangle. Geometrically, it's sum of the areas of corresponding rectangles. Okay. Now the definition. So on which parameters will the S depend? S depends on number one, the number of subintervals. That is n. S depends on n. Second, S depends on the choice of points. x1, x2, xn minus 1. And third, choice of ki's. The point within the interval, subinterval, which point you choose, the value of S will depend on that. Okay. And we are saying that at the moment what we are saying is we can have any width of this subinterval and we can choose any point in the subinterval. Okay. That is the flexibility that we are enjoying at this moment. But eventually we might have some discipline as far as length of the subinterval is concerned and choice of point k is concerned, because if it is random for every subinterval, the calculations are going to be little difficult. So now, what do we mean by definite integral? So definition. For any partition of closed interval a comma b, consider limit sigma r goes from 1 to n, f of kr delta r, when n tends to infinity. Positive infinity, because n is a number, natural number. How many partitions that you are making in such a way that the largest of all the subintervals that is delta 1, delta 2, dot dot dot, delta n tends to 0. Exists. Now let me exists. What exists? Limit exists. Then the function is said to be integrable over a comma b and the limit is called definite integral of f of x over a comma b and is denoted by integral a to b f of x dx. Now that is what is interesting. This sign is something limit in summation from 1 to n. That means this. F of k of x is f of x. Delta of r is dx because n is tending to infinity. That is what is a formal definition of definite integral. It is also called Riemann integral. So this is limit of sum. Limit of sum is very important word here. You are taking sum and then taking limit. We have discussed this earlier in our life, but this is the first time that we are giving a formal definition out of it. When did we discuss this earlier? When we found out when we measured the circumference of the circle, we said you put the pins on the circumference and then tie a rope around and then measure the length of the rope. That will give you the circumference of the circle. But we said every time we have finitely many number of pins, we have finitely many sided polygon with us, and it is really not the circle. And therefore we put the condition at that time that number of pins should be infinitely many large. That is what is captured here. N tends to infinity. Two conditions we put then also. Number of pins should be infinitely many large, and the distance between the two pins should be arbitrarily small. That is, largest of the subinterval tends to 0. Understand this. We discussed while considering the circumference, you put the pins and then find out the circumference by putting a rope around those pins, but then it is a polygon. So we said number of pins should be infinitely many. That is what is captured here. And you cannot put infinitely many pins only between this. I mean, there could be a chance that you can put infinitely many pins here, but you should not do it like that. You should find out the largest subinterval, largest chord, and try to make it small by putting a pin here. The moment you put pin here, the other chord will become larger. Go there, suppose here it is another chord, go there, put a pin here, and go there, put a pin here. Then you find this, go there, put a pin. And if you keep doing this, and number of pins are infinitely many, then you get the circumference. So this is what is the limiting case. We used to say the word limiting case, and that is what is this captured here. In this case, if this limit exists, the way if limit exists, the function is differentiable. Similarly, if this limit exists, we say that it is integrable and the value will be called definite integral of f of x. Okay. Okay. So whatever we have discussed so far has hardly anything to do with antiderivative. This limit symbol that we are using here is not the differential calculus limit symbol. I am just writing it limit because we know that symbol now. But actually it is whatever I am taking it here right now in this notation is explained in this paragraph. Understand that. And therefore, the definition of limit which we wrote is much later compared to what these people have done maybe I think 2000 years before. Archimedes. They have found out the area under the curve using this principle. And at that time, calculus was not there. Antiderivative, much later. So this is very old technique of finding out the area. Break it into the pieces and add. That is what is integration. Okay. परत मला आठवेल असं सांगता येत नाही. Integration is making the curve smooth. Now, what exactly are you doing here is you are finding out area of this rectangle, then area of this rectangle, then area of this rectangle. Different rectangles, okay? And when you are trying to integrate, the word integration, you are trying to, this is two big rectangles. So let me make it break it into two small, and then maybe I will have corrected the area. This rectangle is gone. This is too big. Again, let me correct it. So as you increase the number of intervals n, and as you decrease the width of every interval, you are integrating. So right now, if you look at this curve, it is rough. It is steps and steps and steps. We will not be able to call this as curve by our intuitive understanding of curve. But this is what is the curve right now you are considering while finding out the area under the curve. So if you do n tending to infinity and width of every interval approaching 0, that means what you are doing is you are trying to make it like this. Instead of those steps, you are trying to make it like this. So integration is making the curve smooth. And other side of the story, when we had curve with us and we differentiated, we said, oh, I don't understand how to deal with this curve at this point. Let me deal with the tangent at that point. We took that approach. And that is what is pending. Tangent is the closest approximation of the curve at that point. We will discuss that later on. Okay. So I am saying that it is very difficult to discuss curve at this point. It is easy for me to discuss the straight line. Okay, discuss straight line. Then it is difficult to discuss the curve at this point. It is easy to discuss straight line. It is easy to discuss straight line. It is easy to discuss straight line, and so on. Easy to discuss straight line. So differentiation is making the curve rough. Geometrically, these are the meanings of the two operations, which are, if we consider the second one as derivative, the first one is antiderivative. Eventually, we will say that it is antiderivative. But integration and differentiation are opposites of each other. One is making the curve rough, another is making the curve smooth. Important. Okay. So we can call this S as area under the curve also. So now here one thing is very important, that S is area. Under the curve, we can visualize it as area under the curve geometrically, which we said earlier. Now only problem in that place, I mean in this case, is if your curve is above x-axis, we don't have any problem. This is area. But the moment your curve will go below x-axis, then this will have little problem. If we are talking about area entrapped between the curve and x-axis, then of course this also has to be included, and overall area is going to be greater than 0 or greater than or equal to 0, because this is some area, this is some area, they get added, and greater than or equal to 0. Area is going to be greater than or equal to 0 if we are supposed to find out the area. But if we are supposed to find out some number a comma b, f of x dx, s is equal to, then this is a real number which can be positive, which can be 0, which can be negative. This is real number. Meaning of that, geometrically is area trapped between the curve. Basically area trapped between the curve x is equal to a, x is equal to b, and y is equal to 0. Okay, when we say S is the area under the curve, we mean area entrapped between y is equal to f of x is equal to a, x is equal to b, and y is equal to 0. I mean, if we are dealing with dx, differential dx. If it is y, dy, then maybe this is c, this is d, and area curve is like this. Then you may be talking about this area, f of y, x is equal to c, sorry, y is equal to c, y is equal to d, and x is equal to 0. So you are talking about this area or this area, and how do we find out whether with respect to x or with respect to y? This will tell us this is our real variable, differential of x, subinterval of x, function of x. This is function of y, subinterval of y, and the boundaries are y is equal to c, y is equal. So this integral will be written as integral c to d f of y dy. Okay, this is the sum. So what I'm trying to tell you now is, if in the question, if you are asked to find out area entrapped, word area, then you need to consider all negative areas as positive areas and add up to positive areas and report the total answer. But if you are asked to find out definite integral, then whatever that number you get, maybe positive, maybe 0, maybe negative, you should report. You should not make it positive deliberately. Otherwise, the answer is going to be wrong. So, if we have understood this, let us solve a couple of problems from our old people and then really get into the advanced differential, advanced definite integral. Okay. Now, let me develop the same in little different notation, which eventually we will require. Should keep 56% at least. Okay. Now what we when it comes to actually finding out the area under the curve, it will be difficult if we use the flexibility number one, width of subinterval. Okay, so if width of subinterval can be anything, every time it is changing, then we will be in trouble, because we are supposed to do calculations and get the area under the curve. So for all practical purposes, why do we take the width different for every interval? Because eventually if we are going to make the width 0 every time, then it is good to have the width in the first place equal. So now let me draw a number line again. Let me write down, this is A. 1, 2, 3, 4, 5, 6, maybe. This is B. Okay. So if this is A, I will say this is A plus H, A plus 2H, A plus 3H. And this last one is going to be A plus NH. This will be A plus N minus 1 times H, second last. Is that correct? Take one with H added, 2 with second point. So this is what was our x1, x2, x3, xn minus 1, xn. This is x0 in earlier language. Okay, now every interval has same width. And now, instead of choosing any point between A and A plus H, I can have some discipline there also. Maybe I can choose midpoint, but still for me the calculations are going to be heavy, because the midpoint is going to be A plus H by 2, bad number. A plus H by 2 plus H, 3H by 2, bad number. So maybe I choose K1 as A, K2 as A plus H, and Kn as A plus N minus 1 times H. That is one way I can do. The boundary point I can choose, no problem. Or I may do it like this: K1 is equal to A plus H, K2 is equal to A plus 2H, dot dot dot, Kn is equal to A plus NH. Either way I can do, and I am also free to choose any point in between. It will not make any difference as far as calculations and final answer is concerned, because limiting case is working there. But our calculation simplicity must be available. Therefore, let us check what do we have. A comma B, f of x dx is equal to limit as n tends to infinity. What are we supposed to add? We are supposed to add f of k1 times delta 1 plus f of k2 times delta 2 plus dot 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 plus f of kn times delta n. This is what we are supposed to add, and then take limit as n tends to infinity. That is what is the meaning of definite integral. So putting this into our notation now. Okay. Now, as n tends to infinity, let me write down limit n tends to infinity f of k1. So let us take maybe this case, f of a. What is delta 1? Now, because the width is same, every time it is going to be h plus f of a plus h times h plus f of a plus n minus 1 times h into h, correct? And what do you think will happen if this n is tending to infinity? If n is tending to infinity, the width of the subinterval will tend to 0. So I can convert this limit now into limit as h tends to 0 and h comes out common, h inside bracket f of a plus f of a plus h plus dot 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 plus f of a plus n minus 1 times h times bracket complete up to this point. So this is equal to sigma h, it tends to 0, h times sigma r goes, sorry, limit h tends to 0, h times sigma r goes from 0 to n minus 1 f of voila, a plus r h. And if we would have chosen this, then our formula would have been limit h tends to 0, h sigma r goes from 1 to n f of a plus rh. That push pull also if we can do, and we can do it like that. So this is what is a working formula, because the interval width is same and point which is chosen for evaluating the function is the extremity of that interval. Okay, so now I give you a function and you give me the area under the curve. So question, find area lying between the curve y is equal to x square, y is equal to 0, x is equal to 1, x is equal to 3, using limit of sum. Okay, we are not supposed to use antiderivative now. You are supposed to use this theory that we have developed just now and tell me what is the answer. Oh, talking for 45 minutes. Okay, so if I use this formula, then the area under the curve area is equal to limit h tends to 0, h inside bracket f of a plus h. Okay, before that our limits are 1 to 3, so this is 1, this is 3, so my a is 1, b is 3, and I am making n subintervals. All of them are at equal length. The total number of intervals n, and width of every interval h. So when I multiply n by h, I should get 3 minus 1, which is equal to 2. The fact that I already have with me. So a is equal to 1. So f of 1 plus 1h, 1 plus h, and my f of x is x square, plus 1 plus 2h bracket square plus 1 plus 3h bracket square plus dot dot dot. The last one is nh plus 1 plus nh bracket square. Okay. So now the area under the part curve, area under the curve part is over now. Now it is a calculation of evaluating this limit. It is a limit problem now. So limit as h tends to 0, h inside bracket. What will be this? 1 plus 2h plus h square. What will be this? 1 plus 4h plus 4h square plus 1 plus 6h plus 9h square. And what will be the last term? 1 plus 2nh plus 4n square h square. Right? So limit h tends to 0, h inside bracket. If we collect all ones, then how many of them are there? How many brackets are there? N. Now this, if we take plus 2 common, h common, inside bracket 1 plus 2 plus 3 plus dot 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 plus n plus. Now in the
सर सर ते शेवटच्या टर्म मध्ये 4n स्क्वेअर h स्क्वेअर कसं काय आलं? n स्क्वेअर h स्क्वेअर पाहिजे ना.
पूर्ण पण आहे का? बरोबर. Okay, so what we can take out common from the last? H square inside bracket 1 plus 4 plus 9 plus dot 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 plus n square bracket complete. Okay, now this is equal to limit h tends to 0, h inside bracket n plus 2h sum of n natural numbers, n into n plus 1 upon 2 plus h square sum of squares of n natural numbers, n plus 1 6. Is that right? So now nh is equal to 2. We have nh is equal to 2 with us. So let us try to evaluate this limit. Limit h tends to 0. Suppose we take this h also inside, then first term is nh, which is 2, plus h square n square, 2 to cancel, so h square n square, that is nh square, that is 4, plus h square n. Is that right? 2 to cancel, h square n, out of which nh is 2, 2h. This is about this term. Is this correct? Okay. Plus, now I have h cube. Let me write down h cube. Then h cube n. What is the multiplication of these two guys? 2n square. एक मिनट करने पूरा होने दो मेरा, फिर देखते हैं. 2n square plus 2 plus 1 plus 3n plus 1 upon 6. Okay, limit h tends to 0, 2 plus 4 plus 2h plus, now n cube, h cube is 2 raised to 3, 2 raised to 3 upon 3, that is the first term, plus second term I have n square and 1h, so 2 square h upon 2. This will not be useful because h is tending to 0. Anyway, we calculate plus nh cube. No, sorry, we need not calculate nh. One nh is 2. So 2h square upon 6. So now everything is in h, correct? And h tends to 0. Therefore, the answer is 2 plus 4 plus 8 भागिले 3, which is equal to 7 18 अधिक 8. So the area under the curve is 26 by 2. Okay, what you were saying, Pranav?
So instead of opening up the brackets, we could just substitute 1 power. We could just distribute 1 power of h into each bracket of n.
Yes, and nh. Yes, that would have been better. Yes. So the answer is 26 by 3, which is a finite number, and that is precise area under the curve. There is no approximation. It is equal to everywhere. Okay, so have we really used any antiderivative primitive concept in this? No, it is purely area of rectangles, and because we were aware of summation of natural numbers, summation of squares of natural numbers, we could find this out. Let us solve one more problem. Little easy. Evaluate integral a to b e raised to x dx using limit of sum. Okay, so directly writing the limit h tends to 0, h inside bracket e raised to a plus h plus e raised to a plus 2h plus dot dot plus e raised to a plus nh. nh is equal to b minus a. Okay, so now what is the sum of this? So it is e raised to a plus h is e raised to a into e raised to h. So h into limit h tends to 0, h into e raised to a can be taken out common, and then inside bracket e raised to h plus e raised to 2h plus dot dot plus e raised to nh. So this is geometric progression, and therefore we can h e raised to a, first term is e raised to h, e raised to h is the first term, e raised to nh minus 1 upon e raised to h minus 1. That is the summation, correct? So therefore nh is equal to v minus a, that you can put now. So limit h tends to 0, inside bracket e raised to a into e raised to h inside bracket e raised to b minus a minus 1, that is this term, and then this h upon e raised to h minus 1. Okay. Now h is our variable, so what all things come out? Limit h tends to 0. This is constant, this is constant. E raised to a, e raised to b minus a minus 1 into limit h tends to 0, e raised to h into limit h tends to 0, h upon e raised to h minus 1. Okay, now these are standard integrals, therefore answer is here no h, so e raised to a. Now e raised to b upon e raised to a, so this is e raised to e, sorry e, okay, e raised to a into e raised to b upon e raised to a minus e raised to a. This is 1 into this is 1. This is equal to e raised to b minus e raised to. This is by first principle, limit of sum. And once we prove fundamental theorem of integral calculus, we know antiderivative of e raised to x is e raised to x to be evaluated between a and b. So e raised to b minus e raised to a, which is the same as this. Okay, but this is where, I mean, we are not using any antiderivative so far. We are just using principle of limit of sum, and we are dealing with these brackets because we are good in summation. Okay, now I want you, each one of you, to solve at least one problem in this. Therefore I give you one more problem which is very simple, which we should not solve using this concept, but we will solve between integral, evaluate integral 0 to 1 2x plus 3 dx using limit of sum. आता काढा बघूया, प्रत्येकाने उत्तर दाखवा मला. Okay, answer for this is 4. Using similar principle, you should be able to find it out. Now, okay, so let us go back. Fundamental theorem of integral calculus. Statement I will write and give you some time to prove. If integral a to b f of x dx considered as limit of an infinite sum exists, and if there is a function x. Phi dash of x is equal to f of x, where a is less than equal to x is less than equal to b. Then integral a to b f of x dx is equal to phi of b minus phi of a. Eventually it becomes that simple. Evaluating definite integral is antiderivative at upper limit minus antiderivative at lower limit. It becomes that easy. So this is the statement of the theorem, which is fundamental theorem of integral calculus, and we are supposed to prove it eventually. So I wait for 5-10 minutes. I allow you to explore possibility of writing your own proof, then we will discuss. Let us write down the proof of this. In the interval function phi is differentiable. Hence continuous. Therefore, LMVT is applicable. Applying LMVT for now the interval XR x r minus 1 general interval we take, r goes from 1 to n. We have, and x, all these points are within a comma b. Okay, so any sub interval you take, you can apply any LMVT, and LMVT will tell you that phi of xr minus phi of x r minus 1 is going to be equal to phi evaluated at some key r into xr minus x r minus 1, where x r minus 1 is less than kr is less than xr. Is that correct? That is what is our LMVT. There exists some point here, it dash page. Okay, so where kr is some point between the, up to this point it is correct. Now consider integral a to b f of x dx. As a limit of sum, it is limit n tends to infinity, sigma r goes from 1 to n, f of kr into xr minus xr minus 1. Now it is given that x dash phi dash of x is equal to f of x for every x between a comma b. Okay, and therefore f of kr can be replaced by phi dash of kr, which is equal to limit n tends to infinity, r goes from 1 to n, phi dash of kr into xr minus 1. Correct? But phi dash of kr into xr minus 1 is equal to phi of xr minus phi of xr minus 1. Limit n tends to infinity, sigma r goes from 1 to n, phi of xr minus phi of xr minus 1. Okay, so now you understand that this is going to be limit of when r is equal to 1, this will be x1 phi evaluated at x1 minus phi evaluated at x0, phi evaluated at x2 minus phi evaluated at x1, and so on. So as n tends to infinity, what we can write here is phi of x1 minus phi of x0 plus phi of x2 minus phi of x1 plus phi of x3 minus phi of x2, and so on. The last term will be plus phi of xn minus phi of xn minus 1, and n is tending to infinity. So as many as you want, you can put those terms, and therefore we note that this does not have anybody to, of course we can write outside this, we can write limit n tends to infinity, and this is equal to, inside the bracket if you observe, everything gets cancelled, and finally we get xn minus x0, but xn, no, sorry, phi of xn minus phi of x0, but phi of xn is a, so phi of b minus phi of b. That is what is fundamental theorem of integral calculus. LMVT is helping you out. Telescopic setup is also part of the proof, and hence the job becomes absolutely simple. If you know antiderivative, finding out definite integral is very, very simple. Okay. So definite integral is a real number because you are evaluating phi at b, that is a real number, and phi of a, that is a real number, and the difference of that is your definite integral between a to b f of x dx. Okay, so now let us look at some of the properties or rules. Prove that integral a to b f1 of x plus f2 of x dx is equal to integral a to b f1 of x plus integral a to b f2 of x dx. Okay, 2 or 3 minutes for you to do this. Then second, integral a to b k times f of x dx is equal to k times integral a to b f of x constant term you can take out common, where k is constant. Property number 3. I mean, if first one takes 2 minutes, this should take 1 minute. First one takes 4 minutes, this should take 2 minutes. Number 3. Integral f of x dx from a to b is equal to integral alpha to beta f of phi of t into phi dash of t dt, where x is equal to phi of t, a is equal to phi of alpha, b is equal to phi of beta. ठीक है. And rule number 4. Integration by parts. Integral a to b f of x g of x dx is equal to g dash of x ds is equal to f of x g of x to be evaluated between a to b minus a to b f dash of x g of x dx. Okay, just check whether everything is fine or not. So I think the first and second is going to be very easy. Just define some function phi 1 of x, phi 2 of x, and you will be able to deal with this situation. And we can now use the fundamental theorem of integral calculus. So, and derivative is always available with you. Therefore, first and second. Second is obvious case of first used k times whatever. So maybe I will have to write down proof for third. Before that, let me finish fourth. Fourth is integration by parts. Integration by parts is a trick to get the antiderivative. So when it comes to evaluating the definite integral of the two functions which are in product form, and one of them is easily integrable, we just use the formula and evaluate those functions with the limits a and b, as simple as that. Okay, so I mean there is nothing to prove here except putting these limits over there, because integration by parts was a trick for finding out antiderivative. Okay, so now let me write down 3y LHS is equal to RHS, and see if I can push this. Forget about 4. Let us write down 3. Integral a to b f of x dx is equal to psi of x be evaluated a to b as psi dash of x is equal to f of x, which is equal to psi of b minus psi of a. Okay, which is equal to b is psi of phi of beta minus psi of phi of alpha. Okay, which can be written as psi of phi of t to be evaluated between alpha to beta, which is equal to integral of derivative with respect to dt of psi of phi of t to be evaluated between alpha to beta, which is equal to integral alpha to beta, derivative of this is psi dash of phi of t into phi dash of t dt, which is equal to integral alpha to beta psi dash is psi dash of x is f of x, f of phi of t into phi dash of t. Okay, that is what LHS is equal to RHS. Maybe you write down and check whether. When we proved fundamental theorem, the description of the theorem was f of x is considered to be a limit of sum. There exists a function phi over closed interval a comma b, which is differentiable. So a and b were finite points, and phi as well as f were well-behaved functions in the interval a comma b. So just let me use the diagram and show you what we mean by that. A and B are two good points, finite points on x-axis, and the function is also between A and B. Function is very well behaved. So whatever definition or theorem that we have written or we have proved is for this situation where everything is good. A is good, B is good, f of A is good, f of B is good, and function is well behaved between closed interval A and B. But that is not going to be the case always. So if suppose this, what are the different situations under which we will have to deal with and how do we go about it is what we are trying to discuss. Case 1, this b goes to infinity. A stays here, b goes to infinity. Okay, maybe I will just write down 1 integral a to plus infinity f of x dx. I will not be able to use fundamental because we have defined it for good conditions. So we will have to find out what should be the way out for this. Second uncomfortable situation will be lower limit goes to plus infinity, minus infinity. And the worst condition will be right, because the problem is going to be where do you start, where do you make subintervals, that nh is not finite, so everything will fail. So what is your suggestion in this case? Do we really need to deal with this kind of integrals, or is it okay? I mean, majority of them will be like that. Very few will be well behaved like this. We will have to do something for these irregularities because every now and then we are going to face them. So if you were the responsible person for doing this job, what will you do? Example in this case, which I can give you now, is suppose some function e raised to x, and you know you are going to stop here, say 3, f of x is equal to e raised to x, and you know that this is asymptotic, it will never cross x-axis. So is it possible to find out this area under the curve? Will it be really infinite or finite? Will that limit exist or not? If it exists, then we are interested. If it is not, then okay, we are not interested. Understood? So maybe this case, maybe the case other side, I mean, I start at -3 and this goes to plus infinity. Will I be able to find out this area under the curve? I mean, that is what needs to be considered. That is what we have to deal with in the first place. So once we are done with this, we should be able to deal with these examples. Those are the practical problems. What is your solution? By now we have developed several tools to deal with these situations, and it is simple. It is simple because we have developed all the tools. I will write it as it goes from a to x and limit x tends to infinity. Okay, that is the bypass that we are doing. So as far as this is concerned, from year to year, are we obeying the prerequisites of fundamental theorem of integral calculus? Yes. X is a point, yes, and now that x is dynamic and it is becoming bigger and bigger. So I am considering x, which is a dynamic point, and it is becoming bigger and bigger. A is a finite point, and if possible, I would like to evaluate this number, this real number, which is going to be in terms of x and a. What happens when x tends to infinity? So we have broken it into two parts. One, this is definite integral, it obeys the fundamental theorem of integral calculus. And limit, I mean limit we are taking. If it exists, then yes. Will this give us a real number? Yes, if this is well behaved in terms of getting the limit. Anyway, the definition says if limit exists. So as x tends to infinity, if this value exists, then there is a value for this, otherwise it does not exist. Understood? Similarly, limit as x tends to minus infinity, integral x to b f of x dx, and here what we will do, you break it up in two parts, f of integral minus infinity to a f of x dx plus integral a to plus infinity f of x dx. Now, is this allowed? I think we have not written this. Can I break it into parts? Yes, because integration is addition. Integration is summation. Therefore, I can always break it into the parts, how many parts that I want. So this is valid, this is true. And then apply rule number 2 for this and rule number 1 for this, and we get the answer. Okay, let us see in real life whether this will be useful or not. 1. Find out integral a to infinity e raised to x dx. How much? That is question 1. Question 2. Integral zero to infinity dx upon 1 plus x square is equal to. Okay, I give you 2-3 minutes, then I write that solution, and that is where we stop for the day. Okay, the first one we will write limit x tends to plus infinity integral a to x e raised to x dx, which will be, so now I can evaluate this definite integral, limit x tends to plus infinity e raised to x minus e raised to a. Now, if we really want to evaluate this integral, it is not possible, it does not exist, because e raised to x is a huge number, big number, and this is finite number. So, does not exist. This integral will not give you a real number. Now, if you are writing the answer for this as infinite, then it is not correct, because infinite is not a number. After solving your definite integral, you are expected to get a number. And geometrically, if you see, it is the area under the curve, so it's a finite number, area. And therefore, this is not correct. You should write that limit does not exist, therefore this integral does not exist. Second question, again integral 0 to x, limit x tends to plus infinity upon 1 plus x square. So antiderivative part is concerned, it is tan inverse of x to be evaluated from 0 to x. And then before that, limit has to be taken from x tends to. Okay, so limit x tends to infinity tan inverse capital X minus tan inverse 0. So tan inverse capital X, limit tan inverse capital X as x tends to infinity is pi by 2 minus limit tan inverse 0 as x tends to infinity is 0. Therefore, answer is pi by. Okay, but then this is, yes, theoretically, fundamentally correct. But in real life, you can write it from here, directly from here, saying that tan inverse x to be evaluated from 0 to infinity, which is equal to tan inverse infinity minus tan inverse 0 is equal to pi by 2. Instead of writing this, because we have theoretically got the bypass done, or for all practical purposes, these are going to be your calculations. अरे समझते हैं कहाँ? So these are your improper integrals. Improper integral. Okay. So improper integral of type 1 we have discussed today. Type 2 we will discuss tomorrow, next lecture. What are improper integrals of type 1? Where you expecting these limits, upper limit and lower limit a and b to be finite number, but they are not. Either they are minus infinity or plus infinity, or one of them is finite. So that is what we discussed today. Second irregularity could be, that is type 2, improper integral of type 2 could be, these points are well behaved, a and b are finite points, but suddenly in between the function is not continuous at some point. Then how do we deal with that? Can we really find out area under the curve, etc.? We will look at it next lecture. That is where we stop for the day. Pause.